came up in class. I'll start over because I know the recording probably wasn't going. This question came up in class the other day. Why is HF a weak acid when HCl, HBr, and HI are all considered to be strong acids? And that actually lies in all this explanation about electrons. What happens is fluorine has such a strong bond strength, it's actually more difficult to get that hydrogen off of fluorine. It's a little bit easier to get the hydrogen off of chlorine, easier to get the hydrogen off of bromine, and extremely easier to get the hydrogen off of iodine. That's why HI is a stronger acid than HBr, which is a stronger acid than HCl. Now these will all have still ionization or K values, Ka is greater than 1, so they're still all extremely product favored. They'll all ionize into solution. That is not the case with HF. As you can see, we have the pKa. So if we wanted to find the Ka, we'd say 10 to the negative pKa. That's going to be a very small value. This is going to be 10 to the negative -7, 10 to the negative -9, 10 to the negative -10. Where here we've got 10 to the negative 3.14. So this is still going to have a K value, a Ka value less than 1, making it a weak base. Excuse me, a weak acid. It will go back. That is not a base. Definitely HF is not a base. The F ion by itself would be a base, but HF is a weak acid. Thank you, Ms. Beichner, for correcting me as I sat here and recorded this. Now, what about HNO2 being weak when HNO3 is actually a strong acid? It lies in the same idea. We're dealing with oxyacids, nonmetals bonded to oxygens. They have their special names. We call it nitric or nitrous acid and nitric acid. We don't even say anything about the hydrogens on it. But the acid strength is determined by the number of oxygens bonded to the central atom. The more oxygens that you have, the easier it's going to be for that hydrogen to slip away. In this example, chlorine's not going to be as interested in the hydrogens when it's got 4 other oxygens to deal with down here. Where chlorine can keep a little bit better of an eye on its hydrogen in this situation, a very close eye on it here, and if we had the hypochlorite or hypochlorous acid, there chlorine's only watching onto 1 oxygen and 1 hydrogen. It's much more difficult for that hydrogen to sneak away from that chlorine as it's really high electronegativity value. Where down here the chlorine satisfied, it's like, oh, I've got 4 oxygens, that hydrogen can just go do whatever it wants. One of our strongest, if not the strongest acid that there is, chloric acid. Extremely strong because that chlorine will let go of that hydrogen without even blinking an eye. Anyways, what we end up with is an inductive effect, and that looks at how adjacent atoms attract electrons from another part of a molecule. So since those oxygens and chlorines, they're attracting electrons back and forth from each other, oxygen doing a little bit better job of attracting them, that hydrogen just kind of gets left out all by itself. Nothing really is going on. It's not really a part. Feel like it's kind of left out, and it goes ahead and just leaves. And that's when it becomes an acid, when you have that H becoming an H plus in solution, which then is going to bond to a water molecule. Now, carboxylic acids, why are they Bronsted acids?